Let's take a look at section 4.2, logarithmic functions. If x is bigger than 0 and b is bigger than 0 but not equal to 1, y equal to the base b log of x is equivalent to b to the y equals x. The function f of x equals the base b log of x is the logarithmic function with base b. So this equivalency is what we're going to deal with first in our problems on our worksheet. So notice what this is telling us. As long as x and b are bigger than 0 and b is not 1, then y equal the base b log of x is equivalent to b to the y equals x. So let's take a look at our first problems on the worksheet. Alright, so in these first three problems, we're given an exponential equation, and we want to write the equivalent logarithmic equation. Okay, so if 4 squared is 16, okay, so let's take a look at applying the exponential equation the equivalent logarithmic equation to each exponential equation. So if 4 squared is 16, then it will also be true that the base 4 log of 16 will equal to 2. So the important thing to note is that a logarithm is an exponent. So the base 4 log of 16 is the exponent that you apply to 4 to get 16. So notice the exponent is the logarithm. So for 1b, 5 to the negative third equals 1 over 125 is equivalent to the base 5 log of 1 over 125 equals negative 3. So the thing to remember is the base of the exponent is the base of the log, and the exponent equals the logarithm. So 49 to the 1/2 power is 7 is equivalent to the base 49 log of 7 is the exponent 1/2. So now let's see if we're comfortable going the other way. If we start with a logarithmic equation, are we able to write the equivalent exponential equation? So remember, the base of the logarithm is the base of the exponential equation. The exponent is the logarithm. So the exponent in this case is 2. So when you apply the exponent 2 to 3, you get the input to the log, and we call the 9 the input to the logarithm. So 3 squared equals 9 is equivalent to the base 3 log of 9 equals 2. So the base 16 log of 4 equals 1/2 is the same as 16 to the 1/2 power is equal to 4. Hi,
Hello.
how are you?
So long.
So the base b log of x minus 3 equals 5 is equivalent to b to the 5th equals x minus 3. Now in the next set of problems, we want to evaluate each logarithm without using a calculator. And remember, a log is simply an exponent. So in the first one, the base 8 log of 64 is the exponent I apply to 8 to get 64. So that exponent is 2. So notice 8 to the second power is equal to 64. So notice that's why that logarithm is equal to 2. Here we're saying in B, we're saying what power do you apply to 9 to get 3? And notice the square root of 9 is 3, and a square root is the same as a power of 1/2. So this logarithm is equal to 1/2. And then here we want to know what power do you apply to 4 to get 1/16. Well, remember 1/16 is the same as 1/4 squared. And the properties of exponents say if I want to bring that 4 across the fraction bar into the numerator, the exponent changes sign. So this logarithm is equal to the exponent -2. So 1/4 squared is the same as 4 to the -2. Okay, so there are two special types of logarithms, and these are the logarithms that are on nearly all scientific calculators, and that is what we call the common logarithm, and that's the logarithm whose base is 10. So common logarithms have the base 10. So in other words, if the base of your log is 10, we simply write log. So if I have a base 10 log of x, I simply write log x. So if you see log and there is no base, it's understood that the base is 10. So this is the convention. This is what you'll see. Natural logarithms, as you might expect from our previous worksheet, natural logarithms have the base as e. So whenever the base of your logarithm is our irrational number e, then instead of writing log as the abbreviation for logarithm and the base of e, we write ln. And be very careful that when you're entering these into the computer, you're using a lowercase l and not a capital I. Those two look alike when you're using a computer, but the computer knows the difference and will mark this as wrong if you type capital IN instead of lowercase ln. So just be careful. Okay, so the next set of problems involve writing the exponential equation as a common or natural logarithm. So 10 to the fourth equals 10,000 is equivalent to the logarithmic equation common log 10,000 equals 4. So notice when the base is 10, I use the abbreviation log for logarithm, and the base is unwritten. Here I have 10 to the negative 2 equals 1 over 100. So common log of 1 over 100 is equal to negative 2. Here I have e to the negative fourth equals 1 over e to the fourth. So this is equivalent to ln natural log 1 over e to the fourth equals negative 4. So in each case, keep in mind the logarithm equals the exponent. So similarly here, we want to write each logarithm equation as an exponential equation. So here I have to understand that ln is an abbreviation that I use for logarithm when the base of the logarithm is e. And remember, the log equals the exponent. So this is equivalent to the exponential equation e to the fifth equals k. So the input to the log is what the exponential equals to. So here this is equivalent to b, the common log of 100,000 equals 5, is equivalent to 10, unwritten 10 here is my base, just like above an unwritten e was my base. 10 to the fifth power equals 100,000. And again on 5c, the base is an unwritten 10. The log is the exponent, so I apply the power of negative 3 to this 10, and this equals 1 over 1,000. All right. So remember that some basic log properties that will result that involve 1 is the fact that the base b log of b will equal to 1, because 1 is the exponent to which b must be raised to obtain b. So b to the first power equals b. The base b log of 1 is 0, because 0 is the exponent to which b must be raised to obtain 1. B to the 0 is 1. It turns out logarithmic functions and exponential functions are actually inverse functions. Remember, b must be positive and different from 1. So if I make b to the x the input to the base b log, the result is x, because this is the exponent that I apply to b to get b to the x. If I make the base b log of x the exponent of b, then that result is also x, because the base b log of x is the exponent I apply to b to get x. So if I apply that exponent to b, the result is x. So if f of x is the base b to the x, and if f inverse of x is the base b log of x, then this is the composition function f inverse of f of x. And this would be f of f inverse of x. So let's use the properties, the inverse properties of logarithms to evaluate these expressions. So the first expression says, I'm going to take the exponent that gives 13 when I apply it to 6, and I'm going to apply that to 6. So the result here is 13. The second expression says, what exponent do you apply to 5 to get 5 to the 4th? And the result, of course, is 4. Here, we want to know what exponent do you apply to 12 to get 1? That result is 0, because 12 to the 0 power is 1. Here, what exponent do you apply to 7 to get 7? The result, of course, is 1. All right, here we have the exponent that you apply to e to get e to the negative 4th, so that's negative 4, added to the exponent you apply to e to get e to the 9th. That's 9. So negative 4 plus 9 is 5. In the next problem, I want to graph the logarithmic function f of x equals to the base 3 log of x. Okay, so I have to carefully select the x values that I'm going to use here. So I'm going to make a table of values, and I want to choose x's so that my y is an integer. Well, first of all, I know that if x is 1, I know that the base 3 log of 1 is 0. So I'll be plotting the point 1, 0. Also, I know if x is 3, then y is the base 3 log of 3, which is 1. So I'll be plotting the point 3, 1. I also know if x is 9, y will be the base 3 log of 9. And that's the exponent I apply to 3 to get 9. So that's 2. So I'll be plotting the point 9, 2. And then if I pick 1/3 as my x value, the base 3 log of 1/3 is the power I apply to 3 to get 1/3. And that power is negative 1. So I'll be graphing the point 1/3, negative 1. Oops. So let's plot these points. So when x is 1, y is 0. When x is 3, y is 1. When x is 9, y is 2. when x is 1/3, y is -1. And it turns out that if my base is bigger than 1, my log function will always have this type of shape. And we'll look at graphing that on Mathematica as well. Alright, so here we have a Mathematica window open. Let's use the plot function to plot a log. In Mathematica, log has to be spelled with a capital L, O-G. In general, you write it with a lowercase l. Alright, so what I notice here is I need a bracket because this is a Mathematica function. So I'm going to put that. And if I click on this double arrow that appears, it tells me that if I want to type the logarithm to base e, I just use log and I put the whatever the input is in, and that's all that's needed. Mathematica will understand the base is e. But to do the base b logarithm, I put the base first and then the input. So I'm going to use a bracket. I'm going to put my base of 3 and then my input is x. So this is how in Mathematica I would type the base 3 log of x. And then I tell it I want x to range from -10 to 10. And I want the plot range to go from -10 to 10. Alright, and let's look at the graph. And notice how that's exactly what we have sketched, and that's consistent with what we knew we would get. So when the base is bigger than 1, in this case my base was 3, and you're graphing the base b log of x and b is bigger than 1, then this is the type of picture you're going to see. Notice how, again, that's consistent with the graph that we drew. Now let's look at graphing the graph of the base 1/2 log of x. So again, I want to make a table. So I am going to keep in mind that what I'm doing is I'm picking values of x that are going to give me convenient results for this base 1/2 log of x. Alright, so that's what my y value is going to be. So I'm going to pick x equal to 1. So the base 1/2 log of 1 is of course 0, because 1/2 to the 0 is 1. So I'm going to plot the point 1, 0. Now I'm going to pick two. So the base 1/2 log of 2 is actually -1. And notice that's true because 1/2 to the -1 is 2 to the first power, which is just 2. So I'm going to be plotting the point 2, -1. Let's go ahead and pick 4 for x. So the base 1/2 log of 4 is -2. And again, that's because 1/2 to the -2 is the same as 2 squared, which is 4. Alright, and that's 3 points. Let's look at plotting those 3 points. So when x is 1, y is 0. When x is 2, y is -1. When x is 4, y is -2. So it actually turns out that my graph is going to look something like this. Alright, and let's go into Mathematica and graph that. So the only thing we need to do is copy the code that we put in already and change 3 to 1/2. And we can run this. And notice that's exactly what we see that we obtained. Same picture. So whenever the base of your log is between 0 and 1, your graph is going to have this shape. Okay, so those are 2 things for us to keep in mind. Whenever the base of a log is between 0 and 1, the graph of f of x equal the base b log of x will have this shape, what we see in number 8. Whenever the base of my log is bigger than 1, the graph of f of x equal the base b log of x will take on this shape. Okay, and we want to find the domain of a logarithmic function. Well, you may remember that we said if I have the base b log of x, x has to be bigger than 0. Well, in this case, I don't merely, so I'll just write that. Remember, the base b log of x requires that b is bigger than 0, b is different from 1, and that x is bigger than 0. So that was established when the function was defined. Well, now, instead of having x in this position, we have 2x minus 5 in this position. And it needs to be bigger than 0. So let's add 5 to both sides, and we see that 2x has to be bigger than 5. And let's divide both sides by 2, and we see that x has to be bigger than 5/2. So the domain of f of x is the interval of numbers that are bigger than 5/2, or to the right of 5/2. The 5/2 is not included, so I put a parenthesis beside the 5/2, and I can move indefinitely to the right of 5/2, and I signify an indefinite movement to the right with a positive infinity symbol. So this would be my domain in interval notation. Let's take a look at number 10. And on this problem, we want to find the domain again, but this time our function is a little more complicated. We need x squared minus 3x plus 2 to be greater than 0. And this is a polynomial inequality. So we need to factor this polynomial. X minus 2 times x minus 1 needs to be greater than 0. So our boundary points are the x values, x equal to 1 and x equal to 2. And remember that when I'm solving this type of inequality, I'm dividing the number line up based on these boundary points. And in this particular case, x minus 2 times x minus 1 needs to be greater than 0. So that means x cannot equal 1, x cannot equal 2. So we want to find out what happens to all the numbers smaller than 1, all the numbers between 1 and 2, and all the numbers bigger than 2. Now, first of all, remember that our function, we basically need to make sure that what goes into the function is positive. So we need x squared minus 3x plus 2 to be positive. So let's pick a test number in this interval. Let's test x equal to 0. Here let's test x equal to 1.5. And in this interval, where we can use any number bigger than 2, let's test x equal to 3. So our question is 0 minus 2 times 0 minus 1 greater than 0? And we see negative 2 times negative 1 is 2, and that is greater than 0. So here the inequality is true. All right, here let's do 1.5 minus 2 times 1.5 minus 1 greater than 0. So this 1.5 minus 2 is a negative number. 1.5 minus 1 is a positive number. So we have a negative times a positive. Okay, so all we care about is the sign of this, and this is negative. So a negative times a positive is negative. A negative greater than 0 is a false statement. So all the numbers between 1 and 2 make the inequality false. And then let's look at testing x equal to 3, which is going to represent all the numbers in this final interval. So 3 minus 2 times 3 minus 1, is that greater than 0? So 1 times 2, so 2 really is greater than 0. So this is true. So all the numbers bigger than 2 make x minus 2 times x minus 1 greater than 0. So our solution set to the inequality is actually our domain. So the domain of our function, let me just see. So this was the base 9 log of x squared minus 3x plus 2 is the interval negative infinity to 1, unite it with the interval 2 to infinity. So that's the domain of that function. All right, so these are some of the first ideals that we look at when we look at logarithmic functions in section 4.2.